All right, now we're going to learn more about the Nernst equation and how concentration can have an effect on the potential of a reaction. So remember in the thermo chapter when we learned that free energy could vary in non-standard conditions, but it was still related to the standard free energy, and then we added in the potential RT times the natural log of Q. Well, we have a similar equation for potential. The potential is related to the standard cell potential minus RT over NF and times the natural log of Q. So the cell potential will vary as the concentration of the reaction varies, or as other conditions vary away from non-standard conditions. All right, so E is the non-standard potential in volts, where E0 is still the standard potential. R is the 8.314 joules per mole Kelvin. And temperature is still in Kelvin, represented by a capital T. N is the number of electrons transferred in the balanced chemical equation. And F is Faraday's constant, 96,485 coulombs per mole, or joules per mole volt. Let me go back a minute. We have two different types of units here. Depending on the kind of problem we're working, the way we represent units makes it easier to cancel out the units. So you can use either or. All right, so let's work an example. And I still recommend that you pause the video and see if you can work this. We want to calculate the cell potential, or the electromotive force at 25 degrees Celsius for a cell with this overall reaction. And here we're using the notation where we give the concentrations within the reaction. All right, so first let's determine our cathode and anode. Silver is getting reduced, silver ion is getting reduced to silver solid, so that's the cathode, and zinc is getting oxidized to zinc ion, so that's the anode. And we can use the cathode minus anode equation for the standard cell potential, and if we look those up on the table, we get 0.8 minus a negative 0.76, so the cell potential for this reaction is a positive 1.56 volts. So this is a spontaneous reaction under standard conditions. Now let's figure out what kind of potential we have under these different concentrations. So we're going to use the Nernst equation, and in this equation, Q is equal to the concentration of zinc ion over the concentration of silver ion squared, because remember, it's products over reactants. The solids do not go into the equation, so we leave out zinc solid and silver solid, and that leaves us with the two ions, and silver in the balanced equation has a coefficient of 2, so we have to remember to square that in our expression for Q. All right, so once we plug everything in, we have our standard potential of 1.56, and we're going to subtract. So then we have this big expression here of a bunch of different things, a bunch of different numbers, RT over NF, and don't forget your natural log or your squared. Those are very easy to forget. So you're going to do your natural log and figure out that number, okay, this big number, and multiply these two areas together. And then you're going to subtract from the standard cell potential, where you get a positive 1.32. So we see that compared to the standard potential, our actual potential is a little bit lower. And that's because our product concentrations are high. In this specific instance, a high product concentration actually lowers the potential that can be reduced for the reaction. If we had a higher reactant concentration, then we could probably get a higher potential out of the reaction. All right. With this, we can also look at the graphical relationship. It's set up as a linear relationship where y equals mx plus b, where if you graph these variables, so the x variable is the natural log of Q, the y variable is the cell potential at the specific conditions. So if you were running an experiment, you could try different concentrations and measure the potential and then graph it to determine more about the reaction. So the y-intercept should give you the standard cell potential. And then the slope is going to be related to the number of electrons. So the slope is going to be negative, and then you can use the slope to determine that value. All right, so we're going to have an experiment where we have aluminum solid reacting with lead ion, and we are going to maintain a 1 molar concentration for lead. And then we're going to vary the concentration of the aluminum 3+ and measure the potential. Remember, Q is going to be aluminum 3+ concentration squared over the lead concentration cubed. But since we're holding the lead concentration constant at a concentration of 1 molar, this will be a much easier equation to deal with. All right, so here are a lot of numbers, but here's my experiment. This is how I'm going to vary the concentration of aluminum, and then I'm going to measure the potential. Now, in my background calculations, I have carried these to many decimal places to get better numbers. If you're actually measuring a potential, you may not get very many decimal places, and you see how little the potential is changing here. But I'm trying to give you good data in your example. All right, so I did my experiment, and now for my graph, I need the natural log of Q. So I'm going to find Q by taking the concentration and squaring it, and then I have to take the natural log of that number. So that's where I got these numbers, and I'm going to create a graph. And this is what comes out when I do the natural log of Q versus E, the potential. All right. So the equation of the line should confirm the standard cell potential and the number of electrons for the reaction. So the standard cell potential, remember, it was equivalent to the y-intercept. And the y-intercept here is 1.53. And that is actually the correct value for the standard cell potential. The slope was equal to the negative RT over NF. So we want to solve for N. So if we plug in the slope we have here and set it equal to this, the two negatives will cancel. And then we are going to cross multiply and isolate the variable to solve for N. And I get 5.99, which is pretty much 6 electrons. And that is correct for this redox reaction. Now, if I had used less decimal places in my potential, I might have gotten something like 5.87 for the number of electrons, and I would round to 6. And that is a pretty typical thing to happen with the Nernst relationship.